Hello. Now we are going to look at some circle theorems, so some facts or some interesting ideas that we can derive about circles that can be useful for answering problems that we can be asked. And to figure out the theorems that we need, we are going to use two facts that we already know about triangles. If we have two interior angles, two inside angles, they add up to the opposite external angle. So A plus B equals C. This comes from the fact that this angle here, this bigger inside angle in the triangle, plus C adds up to 180 because it's the number of degrees in a straight line, and A plus B plus the big angle also adds up to 180. That means that C and A plus B must be the same size. So that's our first fact that we need. And the other one is that if we have an isosceles triangle, so we have two sides in our triangle are equal, then the sides opposite the angles equal the opposite sides must be equal. With these two facts, we can derive quite a lot of interesting things about circles. So let's look at how we can do that. If we have lines where we have a corner down here, corner down here, and we go up to the circle and back down to our second point, and we go from the same points to the center and back again, it's very important that the lines here meet at the center and meet at the circle. What we're about to do does not work unless we go up to the circle and to the center, and we end up often with an arrowhead shaped looking thing, though we don't have to. We'll see how this can be drawn slightly differently to give different looking shapes. But what can we do with our tools that we have for triangles to find something, a new tool that is useful for this shape inside of a circle? Well, what we can do is break this arrowhead shape up into two triangles by drawing a line from the corner of the circle through the center of the circle. Having done that, it may immediately jump out at you that we have two of our first situation here, A plus B, C. We have a triangle and we have a line extending out past one of the sides. And we can also see that we have triangles that have equal sides. Let's look at why. This side, and this side must all be the same length because they're just the radius of the circle. They're going from the center out to the circle in each case. So all of these are just the radius of the circle, or radii of the circle. Well, what consequences does that have? Well, this here is a triangle that has two equal sides. So the angles opposite the equal sides must be equal. So I can call this M, and I can call this one M as well because it's the same angle. And these two sides are equal as well. Now these do not have to be the same, but this angle does have to be equal to this angle here. So opposite, the angles opposite our equal sides must be the same in both cases. Well, what can we say about our angle outside here? Well, it must be the angle M plus M in the same way as C is A plus B. We add the two inside angles and it must give us the outside angle for the reason that we already talked about. So this must be the size 2M. M plus M is 2M. And this must be the angle N plus N is 2N. So what do we now know? Well, this overall angle here, which we can call X, and this overall angle here, which we can call Y, what can we say about those two overall angles? Well, X is the angle M plus N, and Y is the angle 2M plus 2N. Well, what can we note about this? Y is twice as big as X. So Y is equal to 2X because Y is 2 times M plus N and X is just m plus n. So keeping our equation going, that would be 2 times m plus n. So that's our x, and this whole thing is our y. So the angle going up at the circle is half of the angle at the center, or the way that we often say it is the angle at the center, y, is twice the angle at the circle, x. And we can see that we derive this directly from these facts that we already know about triangles. A whole bunch of different things come from figuring out this fact that the angle at the center must always be twice the angle at the circle. One of the things that happens is if you have a triangle sitting inside of a circle, and the base of the triangle is the diameter of the circle. So we go across here and we're going through the center of the circle. So our dot here is the center of the circle. What consequence does that have? Well, this is still corners. We have our little corners standing here, and we go up to the circle and back down again. It looks a little bit different because 2m plus 2n is going as a straight line. It's going straight through the center instead of having the arms going down like this and then going up like we did for our arrowhead shape. But the same fact works out. We can do exactly the same derivation here. The angle here is twice the angle here. Well, this is a straight line. So what angle must be going on in a straight line? It must be 180 degrees. So let's use what we figured out here. We know that the angle at the center is 180 degrees. So the angle at the circle must be half of that. So 2m must be 180 degrees. This angle must be twice as big as this angle. So m is just going to be half of that. It must be 90. So if we ever have a triangle sitting in a circle and it goes through the center of the circle, so effectively one of the sides of the triangle is the diameter, and then it goes up and touches the circle, this angle in here, which I've labeled m at the moment, must always be 90. And it can be an interesting thing to construct these triangles and see that this must always happen. If you draw in a diameter line and then try to draw straight lines up to the circle and then back down to the other end of the diameter, no matter what you do, you always end up with a 90-degree angle up at the circle, for the reason that we derived here. That it always, regardless of how you try to draw your triangle going up to the circle and then back down to the diameter again, you're always having the 180 degrees in the straight line. You always end up with 90 degrees here. And the opposite is also true. If you can see that the angle up at the circle is 90 degrees, then you know that this line across here goes through the center, that it is the diameter of the circle. So, another fact that we can derive from this is if we had two of these arrowhead shapes, both standing at the same corners down here, like we do here, we would say that they were standing on the same arc. A section of the circumference is called, or a part of the circumference is called an arc. If they're standing on the same arc, if the corners come down to the same point, then these two angles up here must be equal to each other. And we can think about why. If we take the green one here, and we go up to the circle, and we also went from that to the center, well, that means that at 20 degrees must be half of the angle that is in here, so x must be 40. So x must be equal to 2 times 20. The angle at the center must be double, or twice the angle at the circle. So x must be equal to 40 degrees. And y has to be half of the angle that's at the center. So y has to be, or 2y, has to be equal to x, has to be equal to 40. So 2y is equal to 40. So we divide both sides by 2. Y must be equal to 20 degrees. And any two or more points that we go up, so we could draw up here and go back down to the same point down here, same ends of our arc, and all of those angles that come up to the circle must be 20 degrees, because they're all half of this angle at the center, x, which is 40 degrees. So we can get questions in lots of different styles, but if we see our diameter line, or if we see 90 degrees coming up here, we know that we're going across the diameter. If we're standing on the same arc, we know that the angles up in the corners that are touching the circle must be equal to each other, and we know that the angle at the center is twice the angle at the circle, and that's what's giving rise to all of these other useful things that we can use for problem solving in geometry. So that is what we need for now.